PPTC 121. Power Plant Steam Systems Session 5. This session includes firing techniques, furnace draft, fluid bed boilers, combined cycle plants, and nuclear plants. Agenda: Spreader-Stoker advantages and disadvantages. Pulverized coal firing advantages and disadvantages. Understand balanced draft furnace design and the purpose of ID and FD fans. Understand the advantages and disadvantages of a fluid bed boiler. Define a bubbling fluid bed and a circulating bed. Understand why fluid beds have fuel flexibility. Understand the operation of a hot cyclone separator and a cold cyclone separator. How do you control emissions on a fluid bed boiler? Nitrogen oxide, SO2, and particulates. Understand how much coal is needed in the modern boiler to produce how much steam. When is an economizer needed? Understand what a combined cycle plant is, and what the advantages and disadvantages are. Define thermal efficiency. Define a heat recovery steam generator or HRSG. Understand the basic operation of a nuclear plant. Define a pressurized water reactor and a boiling water reactor. Why are nuclear plants receiving favorable attention? Review the differences between fossil-powered plants and different types on nuclear plants. Coal firing techniques. There are several types of boiler firing: spreader-stokers, pulverized coal, and cyclone firing. Spreader-stokers. Spreader-stokers of the traveling gate type are probably the most popular stoker application with industrial boilers because of their relative simplicity, low maintenance, and ability to respond to load variations. They are not used on large utility boilers. They, however, have a high particulate emissions emission rate. Stokers firing is extremely sensitive to fuel size, segregation, and moisture. Pulverized coal firing. Pulverized coal firing helps achieve minimum carbon loss, lower excess air, and higher operating efficiency. It has the following disadvantages. The practical lower limit is steam flows of 200,000 pounds per hour, and requires a high-efficiency ash collection system. See page 102 in your book. A pulverized coal-fired boiler is an industrial or utility boiler that generates thermal energy by burning pulverized coal, also known as powdered coal or coal dust, since it is as fine as face powder in cosmetic makeup, that is blown into the firebox. Cyclone firing. Cyclone furnaces were designed to take advantage of four things: lower fuel preparation time and costs, smaller, more compact furnaces, less fly ash and convective pass slagging, and flexibility in fuel types. However, they produce a very hot flame, which produce high NOx emissions, and as such this becomes a major disadvantage. A cyclone furnace consists of a horizontal cylindrical barrel attached through the side of a boiler furnace. The cyclone barrel is constructed with water-cooled, tangential-oriented tube construction. Inside the cyclone barrel are short, densely spaced pin studs welded to the outside of the tubes. The studs are coated with a refractory material, usually silica or aluminium-based, that allows the cyclone to operate at a high enough temperature to keep the slag in a molten state and allow removal through the tap. Furnace draft is the difference between atmospheric pressure and the pressure existing in the furnace or flue gas passage of a boiler is termed as draft. Draft can also be referred to the difference in pressure in the combustion chamber area which results in the motion of the flue gases and the airflow. Types of furnace draft are 1. Natural draft, when air or flue gases flow due to the difference in density of the hot flue gases and cooler ambient gases. The difference in density creates a pressure differential that moves the hotter flue gases into the cooler surroundings. 2. Forced draft, when air or flue gases are maintained above atmospheric pressure. Normally it is done with the help of a forced draft fan. 3. Induced draft, when air or flue gases flow under the effect of a gradually decreasing pressure below atmospheric pressure. In this case, the system is said to operate under induced draft. The stacks or chimneys provide sufficient natural draft to meet the low draft loss needs. In order to meet higher pressure differentials, the stacks must simultaneously operate with draft fans. And 4. Balanced draft, when the static pressure is equal to the atmospheric pressure. The system is referred to as balanced draft. Draft is said to be zero in this system. Furnace pressure. Pressurized versus balanced draft. Pressurized furnace eliminates the ID fan, saving power and floor space. The associated maintenance on the fan is saved. The forced draft fan must be larger, and this approach works better for oil and natural gas units. Boiler setting must be pressurized, and as such there is a need to eliminate flue gas leaks. Balanced draft makes furnace observations simpler, however ambient air leaks into the furnace. Here is an example of a forced draft boiler or pressurized furnace. Notice the lack of an induced draft fan. Here is an example of an induced draft boiler, where the boiler pressure runs less than atmospheric pressure. Fluid bed boilers. These boilers improve the combustion process by allowing flame temperatures to exist at 1500 to 1600 degrees, rather than 3000 to 3500 degrees. The lower flame temperature reduces NOx emissions. Fuels required must be better than 2,500 British thermal units per pound with a high ash and lower moisture content. There are two types of fluid bed boilers. Bubbling fluid bed (BFB). Combustion occurs mostly in the bed because of lower air velocity in the bed and larger fuel. Circulating fluid bed (CFB). These units are designed to have more particles blown from the bed than bubbling bed. The particles are collected by a particle separator and returned to the furnace. Fluid bed boilers have these advantages. Due to lower flame temperature, lower NOx, no SCR needed. Limestone (CaCO3) can be introduced to the bed to control sulfur dioxide. Better flue flexibility. Lower heating value fuel. Lower fly ash production, and less coal preparation with 1/4 inch coal. Types of fluid bed boilers. Bubbling fluid bed has relatively low velocity with coarse bed particle size. Circulating fluid bed has higher velocity with finer particle size. The primary difference between the BFB boiler and the CFB boiler is that with a BFB the air velocity in the bed is maintained low enough that the material that comprises the bed except for the fines is held in the bottom of the unit. Types of fluid bed boilers. Circulation fluid bed advantages. It burns low quality and less costly fuels. It offers greater fuel flexibility. It reduces the cost of fuel crushing because of coarser fuel. And it has lower capital costs because of less pollution control equipment in some areas. Here is a bubbling fluid bed boiler. And here is a circulating fluid bed boiler. Next I would like to talk about combined cycle plants, which is pictured here. This type of plant combines the use of combustion turbines and a steam plant. The combustion turbine generates electricity by connecting the output shaft to a generator. The hot exhaust gases are then diverted into a heat recovery steam generator to boil water and send the steam to a steam turbine with its own generator. These are the advantages of combined cycle plants. Modular construction results in the installation of large plants in 2 to 3 years. They have very high thermal efficiency. Thermal efficiency is the ratio of the heat or power that is recovered from a process divided by the heat that is placed into a process times 100%. They have rapid startup, 5 to 10 minutes from no load to full load. Efficient use of high-temperature exhaust temperatures making cogeneration useful, and low NOx and CO emissions. And here is one disadvantage. The operating cost can vary widely with the highly volatile price for natural gas. Now nuclear steam generation. Nuclear power worldwide amounts to 20% of electric generation. 30% in Japan, 80% in France, and 44% in Sweden. The sizes range from 500 to 3,900 MW. The capacity factor, or the actual generation divided maximum generation over a period of time, is normally over 90%, and they are emission-free. The reactor consists of a core, which is the heart of the reactor, and it contains the uranium dioxide pellets, which is the fuel. The fuel uses a fissionable isotope U-235 and some U-238. The reaction is controlled by the moderator. The moderator can be made of graphite, ordinary water, or heavy water. In the pressurized water reactor, water is used as both the moderator and the coolant. The water is kept under pressure in the reactor vessel and the primary system. The reactor vessel is pumped to a heat exchanger, steam generator, which converts the water to steam. The steam is then used to power a turbine generator. Here is a drawing of a pressurized water reactor. You can see the reactor, the steam generator, the turbine generator, and the condenser. In the boiling water reactor, water is used as both the moderator and the coolant. The water is allowed to boil in the reactor vessel. The steam generated passes directly to the turbine generator for the production of electricity. Here is a drawing of a boiling water reactor. You can see the reactor, the turbine generator, the condenser, and the reactor feed pump. Nuclear power is favorable. Nuclear power plants are reliable and produce power at a low cost. They have a capacity factor of over 90%. Nuclear power fuel prices are stable, and nuclear power plants do not have emission concerns. Most communities support the plants because they have high-paying jobs, support clean air, and have significant property tax contributions.